What if I told you Japan is building a train so advanced, it doesn't just run through mountains, it seems to fly through them? The moment the wheels disappear, this machine stops behaving like a train and starts looking like the future.
At speed, it levitates, floating above the track on invisible magnetic force.
At 603 kilometers per hour, it became the fastest train ever built to travel on land.
And the most unbelievable part is this. Most of the railway doesn't go around the mountains. It goes straight through them.
Connect Tokyo and Nagoya faster than ever before, Japan chose the hardest possible path, a direct line through solid mountain.
What started as a $9 billion vision has now surged to roughly $72 billion.
The deeper they pushed into Japan's geology, the more the mountain pushed back.
Inside this train, superconducting magnets cooled to extreme temperatures make levitation possible. And astonishingly, one political decision was enough to stall this entire megaproject for years.
To understand this story, you have to go back to 1964, when Japan changed the world with the original bullet train.
The Shinkansen was revolutionary, but Japan quickly began asking a new question. What comes after success?
The existing line became one of the busiest rail corridors on Earth, leaving very little room for future growth.
The old route bends around geography. The Maglev route cuts through it.
Research into this system began decades ago, long before most of the world could imagine a levitating train.
It took more than 6 years to turn early equations into a railway that could actually carry passengers.
The first real proving ground came in Miyazaki, where Japan built an early test track to see if the idea could survive reality.
This was not just a train test. It was a test of whether levitation itself could work reliably outside the lab.
When the train lifted from the track, Japan had its proof. The principle worked.
Levitation was no longer theoretical. It had become an engineering system.
But proving the train was only the beginning. The real challenge was the mountain range waiting ahead.
Before full construction, engineers spent years studying the Southern Alps to understand what kind of rock they were facing.
Some sections would pass under more than a kilometer of mountain, under intense pressure from the rock above.
This route crossed fault zones, underground water, and ancient rock, unlike anything standard rail tunnels were built for.
After decades of research, the project finally received full approval to move from concept to construction.
The next step was Yamanashi, a longer, more realistic test line built to prove the complete system.
Here, engineers refined the brutal rhythm of tunneling. Drill, blast, clear, reinforce, and repeat.
Because for a levitating train, even tiny errors matter. The guideway must stay accurate to the millimeter. These coils are the heart of the system, handling levitation, guidance, and propulsion all at once.
Unlike a normal railway, the real motor isn't inside the train. It's built into the guideway itself.
Every kilometer had to be transformed into a giant electric machine before a train could even begin to float. That meant building a power system capable of feeding enormous amounts of carefully controlled electricity into the track.
At the control center, every coil, every sensor, and every meter of train position is monitored in real time.
When the first real test train arrived, it looked less like rail transport and more like a machine from another era.
No overhead wire, no exposed drive system. Almost every visual cue of a normal train had disappeared.
Then came the defining moment. The tires pulled back and the train rose into levitation. Within that testing era, the system shattered expectations and set a new speed benchmark.
Before commercial service even existed,
thousands of people were allowed to experience the technology firsthand.
Once construction began on the actual line, the project instantly became one of the largest rail undertakings in history.
In Tokyo, engineers had to build deep below an active station without interrupting the trains already moving above it.
First step underground was not excavation, but creating retaining walls strong enough to hold the city in place.
The tunnel boring machine was so massive, it had to be assembled underground like a mechanical puzzle. At its cutting face were dozens of hardened discs built to grind through some of Japan's toughest ground.
As it moved beneath neighborhoods, people above barely felt anything at all. Behind the machine, ring after ring of concrete lining locked the tunnel into shape. Every meter forward created mountains of material that had to be carried out without slowing the excavation.
Even changing the cutters became a dangerous operation, performed under intense pressure at the tunnel face.
To reduce surprises, engineers probed the mountain ahead, trying to learn what the rock would do before the big machine reached it.
But the mountain refused to behave like the models. Ancient fractured rock made prediction extraordinarily difficult.
In the worst sections, they had to abandon one method and switch to a slower, more flexible tunneling strategy.
That method was slower and more expensive, but it let engineers react to the mountain, one section at a time.
Under huge overburden, the surrounding rock could squeeze the tunnel like a vice if reinforcement was not immediate.
So crews added steel ribs, rock bolts, and shotcrete in carefully timed layers to stabilize each opening. Then came groundwater, one of the most relentless enemies of any deep tunnel. To control it, engineers sealed pathways, diverted flows, and redesigned sections where needed.
Even the rock removed from the tunnel was reused, turning excavation waste into part of the structure itself.
Once the excavation was stable, permanent lining transformed rough tunnels into finished infrastructure.
Massive vertical shafts were sunk through the mountain to provide ventilation, access, and emergency escape routes.
This wasn't one construction site. It was dozens of major sites running at the same time, all feeding the same national vision.
Some stations were carved directly into the mountain.
Cathedral-like spaces hidden deep underground.
Instead of rows of columns, the mountain itself became the structure through carefully engineered anchors. After tunneling came an even more delicate phase, installing the guideway with microscopic precision.
For a train that levitates at extreme speed, even a 1 millimeter error can matter over distance.
Hundreds of thousands of coils had to be positioned with extraordinary consistency by skilled human hands.
Even the nose had to be perfected, because entering a tunnel at high speed creates a violent pressure wave.
Its shape was refined through years of airflow testing until the pressure spike could be controlled. Inside each superconducting magnet is wire wound with astonishing precision, layer after layer.
That magnet sits inside an insulated cryogenic system designed to keep it unimaginably cold.
Liquid helium cools the system to temperatures where electrical resistance nearly vanishes.
At that point, the magnet becomes superconducting, and the train gains the ability to levitate efficiently. At lower speeds, it still uses tires. Then above a threshold, the wheels retract, and levitation takes over automatically. A high-speed tunnel entry can create powerful air pressure changes, so passenger comfort had to be engineered as carefully as speed.
Inside, the cabin feels surprisingly normal, because the most complex engineering is hidden beneath the surface.
Thousands of data points are monitored continuously so that no anomaly goes unnoticed.
Every full-speed success began with careful low-speed testing,
where each subsystem was verified step by step.
As speeds increased, the key transition came alive, the instant when rolling motion became floating motion.
Each milestone confirmed that the physics was real, repeatable, and scalable.
Not every test went perfectly. At one point, a magnet failure forced the safety system to intervene. But this is where great engineering shows itself. Find the cause, redesign the weakness, and test again.
Japan also built the system to survive seismic risk, with guideway geometry that helps physically contain the train.
Every test run produced enormous amounts of data, turning each day of operation into a lesson for the next.
When two trains pass at combined speeds above 1,000 kilometers per hour, even the air becomes part of the engineering problem.
Then came the record that captured global attention: 603 kilometers per hour.
What makes that speed remarkable is not just the number, but the smoothness passengers experience inside.
At operational speed, the system can rival or beat short-haul air travel on energy efficiency per passenger.
Longer test sections allowed the system to move from isolated experiments to something closer to real-world railway operation. Behind the scenes, a dedicated maintenance world keeps the trains, magnets, and cryogenic systems ready every day. Even evaporated helium is captured and reused, because efficiency matters at every level of this machine.
Then the project hit a new obstacle, not speed or geology, but water.
Officials feared tunneling could affect regional water supplies, and that concern was strong enough to stop progress.
To solve it, engineers designed systems meant to return the water they intercepted back into the watershed. But every year of delay stretched the schedule and multiplied the cost.
When leadership changed, markets immediately understood what it might mean for the future of the project.
After years of waiting, the first signs of renewed progress returned to the blocked section.
This railway is also being designed for a country that lives with earthquakes, using sensors to react before the danger fully arrives.
Behind every tunnel and every kilometer are tens of thousands of workers, building a line many may never ride themselves.
Not all of the route is underground. Above ground, the same precision continues across bridges and elevated structures.
At 500 kilometers per hour, controlling noise becomes another form of engineering, and Japan has pushed it impressively low.
Now this project sits inside a larger race, where speed alone is not enough. Being first to launch also matters. If Japan finishes this vision, Tokyo and Nagoya will feel dramatically closer, and the train that flies through